Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about RC circuits, circuits that have resistors and capacitors, and we're going to focus on them in the steady state as opposed to the transient analysis, what happens as a function of time, which will come up in our next lesson. So our objectives include calculating equivalent capacitance for capacitors in series and parallel configurations. We've done that before, we're just going to review it a little bit. Describe how stored charge is divided between capacitors in parallel. Determine the ratio of voltages for capacitors in series. Calculate the voltage or stored charge under steady-state conditions for a capacitor connected to a circuit consisting of a battery and resistor network. And finally, sketch graphs of current, stored charge, and voltage for the capacitor or resistor in one of these RC circuits. So very quickly, let's review capacitors in parallel. We know capacitors store charge on their plates, and capacitors in parallel can be replaced with an equivalent capacitor. And we talked about doing that. The equivalent capacitance for capacitors in parallel is just the sum of the individual capacitances. And for capacitors in series, the charge on them must be the same, and they can be replaced with an equivalent capacitor following 1 over the equivalent capacitance is 1 over C1 plus 1 over C2, and so on and so on. So, as we get into RC circuits specifically then, RC circuits are comprised of a source of potential difference to make the current flow, a resistor network, and 1 or more capacitors. We're going to look at RC circuits from the perspective now of what happens when they're first turned on and what happens after a long time. And what's in the middle we're going to kind of leave till the next lesson, at least for starting out. Now, the key to understanding RC circuit performance: uncharged capacitors act like wires, charged capacitors act like opens. Gotta know these two facts. It's going to help you immensely with your analysis of capacitor circuits. So let's take a look at charging an RC circuit. Here we have a source of potential difference, some VT. We've got a resistor R. We have a capacitor C, and we've defined the positive and negative side of our capacitor. And at time t equals 0, we're going to close this switch and see what happens. Now, initially, the capacitor acts like a wire when it's uncharged. So if we were to take a look at this, and we're going to follow a Kirchhoff's voltage law path around that way, I could write that minus VT, because starting here we see the negative side first, plus IR plus the voltage across our capacitor is going to equal 0. All right, well, we also know that our capacitor is charge divided by voltage across our capacitor. Therefore, the voltage across our capacitor is Q divided by C. So I can rewrite my equation as minus VT plus IR plus Q over C must equal 0. But we also said at time t equals 0, when we first close that switch, the charge on our capacitor is going to be equal to 0. It's uncharged. So that simplifies our analysis a little bit, and we have minus VT plus IR equals 0, which implies that VT equals IR. Probably not a surprise. VC, therefore, must equal 0. So if we were to do our plot of the different things we have down here, initially, the current flowing through our circuit is going to be VT over R. So we can make one point over here for the current through our circuit and call that VT over R at time equals 0. We also know the charge on our capacitor at time equals 0 is equal to 0. And we also know the voltage across our capacitor, because Q is 0, must start at 0. So there's our initial analysis. Now let's take a look and assume that the thing's charged up. It's been a long time, and a long time is something we're going to define here in a couple minutes. But now, after a long time, the switch has been closed for a while. The capacitor now acts like an open. It doesn't allow current to flow. So as t approaches infinity, as it gets very big, and we apply Kirchhoff's voltage law to the same loop, go around the same way, I have minus VT plus IR plus Vc equals 0. But now, since I equals 0, we find that Vt equals Vc. No current flowing, so we have the same voltage across the source of potential difference that we do across the capacitor. So our current went down to 0. It's going to follow a path something like this, an exponential decay up to this point that we're going to call 5 tau, or 5 time constants. And we'll talk about exactly what that time is here in a moment. Now, the capacitor must be charging up during this time. When it's fully charged, we know that it must have a charge of CVT on it. So I'm going to draw an asymptote in here at CVT when it's fully charged, and it's going to have an exponential increase toward that value, getting really close to it at about 5 tau, or 5 time constants. And the voltage across our capacitor, well, it started at 0. We know after a long, long time, we just determined that that was going to be equal to Vt. So we're going to follow that same asymptotic relationship, getting very close when we get to about 5 tau. How about if we were to